Welcome back. In the previous session, we looked at part 4 of the compression members and I think chapter E, which is again compression members. We talked about every little detail. If you have not watched the session, please go ahead and watch it. It's absolutely free. In today's session, we'll be doing a bunch of worked out examples. Idea is to see how we can apply the learnings that we had from previous session. Okay. Again, the main intent of this channel, all these codes are pretty complicated, very heavy on text usually, but very light on visuals. My goal is to keep these dense, complex clauses. You take these dense, complex clauses and then bridge the gap with the simple hand-drawn sketches. So you'll be seeing me not doing any fancy presentation. Everything is black and white, no colorful pictures, no formal presentations. This is as if you're in an office setting or an exam setting and you just have access to the code and you have access to the problem and you're trying to scroll through different sections of this code and trying to solve the problem at hand. Okay, I'm trying to transform all this abstract information into clear mental images. This visual association makes it much easier for you to recall specific requirements when you are under pressure, in an exam setting, for example. In this video, we're breaking down part 4 and chapter E, compression members, to see exactly how the theory translates into physical form. We will actually be doing a bunch of examples on these things, but then we went through part 4 and we also went through chapter E in detail in the previous session. Okay. So let's get started. I will open up the first problem. We'll see what we have here, and then go from there. Okay, I'm pulling up information here. Let's go to the. All right. So that is our first problem there. Looks like we have a HSS section. And then let's see what we have. We have so here is the problem definition. We have an HSS 8 by 8. So that means we have a square HSS 8 by 8 inch, right? And the wall thickness is 5 by 16. So the wall thickness of this HSS is 5 by 16. There is a factored load that has been applied, and it is a specific grade of steel A501, grade A in this example. And the column effective length is given to us, which is that means our life is a little bit easier. We don't have to calculate the effective length factor, multiply it with the length and all that. But this is a starting example. We will see an example wherein we have to calculate the effective lengths and all that. Okay. So HSS section again, 8 by 8, subject to a certain load of a certain grade steel and a certain effective length. The question is asking us to see if this section is adequate or not. Okay. So solution. First thing we will do is pull the member properties. So you go to let's see if I can. I think you know how to pull the member properties, right? So you'll have to go to table 1- something, which for HSS sections, and you pull all the member properties of HSS 8 by 8 by 5 by 16. Okay. And if you pull those information, you will see that the B by T value is 24.5. The H by T value is 24.5 because this is a square section. B by T meaning, let's say this is the HSS section. That's the B and that's the T value there, right? And this is useful to find out to see if you have slender flanges or anything like that. The elastic section modulus 21.4. Z about the strong axis or weak axis, both are same in this case, 25.1. The gross section area, that is this hatched area here, is 8.76 inch square, right? and your radius of gyration is 3.13. So all this is um, from part 1 of the table. So let's see, we go to here, part 1, and then get into the tables. You go to the square shape HSS, it's right there, and then you go to HSS 8 by 8, right? HSS 8 by 8, and you see this is HSS 8 by, right? And then go by your, I think we have a 5 by 16, so you'll have to pick up information from this particular row here, okay? Again, this is table 1.1-12, right? So that's the information from the table. Then we'll have to um, check the adequacy of the column for factored axial load. You know that columns under compression, the phi value is 0.9, unlike concrete. In concrete, our compression members have 0.65 as our strength reduction factor, whereas in steel, we have it as 0.9. So if you have an HSS section, again, you can refer to the code here, then it is either governed by section E7 of the code or E5 of the E3 of the code. Okay, E7 is when you have slender members, meaning if these elements are slender, you have 8 and you have a very thin section, then you get under the E7, and then you will have to check for lateral buckling, and you also have to check for flexural buckling. Okay, but if you don't have slender members, then you just have to check for flexural buckling here. Okay. So let's compute our lambda. Let's compute our lambda r, right? So this is the upper limit of your this is the upper limit that defines your slenderness ratio. I'll go to this section, but we talked about it in the last time. It is nothing but E by Fy. You don't have to remember it. There is a table in the code, and you get into compression members. Then I think it is in section B4. You get into the compression member, and based on your shape, you have HSS shape here. You pick up your lambda r, which is the upper limit value. You calculate that 1.4 times square root of 29 10 power 6 by your Fy. So what is my Fy? That is the question, right? We were given that this steel is A501, but what is your Fy? How do you get it? What is your Fu? Where do you get those? Where do you get that information from? Okay. Again, you go to the code, and then this is usually in a table, which is, go to, this is table general. You go to this part here, and then you scroll all the way down. You'll see the specifications here, correct? And you see the ASTM specifications for various structural shapes. So you get into that particular table. We are the question, the problem statement says it's an A501 grade A. That means your Fy is 36 and your Fu is 58. So this is a very important table that you need to quickly pull up in an exam setting. Obviously, you cannot remember all the grades and then Fy and Fu values across all the grades. You don't have to remember, but you will have to make sure you know where this thing is tucked in under these bookmarks here. Okay. So 36 and 58, with those numbers, we'll go back here, and then Fy is 36 KSI, 58 KSI. Okay. So we got our Fy and Fc, so that means we can go ahead with computing this slenderness limit to 29 into 10 power 6 by our 36 times of 10 power 6, and you calculate this value, it comes to 39.73. Now, why are we calculating this lambda r? We want to compare our b by t with this lambda value, right? That means our b by t if the b by t is less than this particular lambda value here, then we don't have slenderness related issues. But if the b by t is greater than that lambda there, then we have slenderness related issues. Okay, and then we'll have to get into the code. So the b by t again for this section is given as 24.5. So that means b by t, which is 24.5, is less than 39.73, which is my upper limit lambda r. That means I don't have slenderness related issues. So if I don't have slenderness related issues, then I don't have to check the local buckling business because my members are not slender. I only have to worry about um, flexural buckling, right? And flexural buckling, we have seen it. So flexural buckling is nothing but you calculate your nominal value as FCR times of A gross. Again, this is there in the code. For example, if you go here and you go to chapter E, right? So this is design of compression members, and um, we are in E3 because we are talking about members without slender elements. Again, we talked about all this in detail in the previous section, right? But if we go here, if we have to talk about real quick, then PN is nothing but FCR, F critical times of A gross. Your FCR depends upon the FCR is a function of your um, Fy by Fe value, right? You can either check Fy by Fe value or you can check this particular value here, right? And if this particular value LC by R of your column is less than a certain limit, then you find out your FCR using this equation. But if your L by R value is greater than, if your L by R value here is greater than a certain limit, then you find FCR through this particular equation. And all this is doing is this is your this is your FCR, let us say, on the y-axis, and this is your lambda, say, on the x-axis. So that limit there is 4.71 square root of E by Fy, right? So if you fall on this side, then you have to I mean, if you plot the curve, look something like that. If you fall on this side here, um, elastic buckling is happening. If you fall on this side here, inelastic buckling is happening, right? So FCR value has to come from two different curves. This is curve 1 here, right? And this is curve 2. This is curve 2 here, right? So and that is what is happening here. You have to figure out if you fall on the left on this side or this side of this particular lambda value, correct? And that's what we are exactly doing. So we'll go ahead and compute our LC by R and this ratio, and then try to see where we fall. Okay. So going back to the problem again, so we have now seen FCR. FCR is FCR times AG is my PN. Okay. So I calculate my LC by R. LC by R, what is my length of the member is 24 feet times 12, 24 inches. By what is my R ratio? Slenderness ratio, we noted that from the property table, that amounts to 92.012. Okay. Now compare that. Compute the 4.71 root F by Fy by Fe, root E by Fy. So that is nothing but 4.71 times square root of E is 29 10 power 6 for steel. By your Fy, we found out that it is that particular value from your table 4. So this comes to 133, right? So LC by R is less than 4.71 square root of E by Fy. That means we fall on this side. This is my 4.71 square root of E by Fy. We fall on this side. That means inelastic buckling is going to happen. That means when the buckling happens, the stress is I mean things have yielded in this on this side of the line, and then the structure will not bounce back to its original shape if you remove the loads. Okay. So once we have decided that this is what is happening, right, on which side of the curve we fall, then we go ahead and compute our FCR value, and FCR value from that equation is 0.658 power Fy by Fe times your Fy value. Now, how do you compute Fe, right? So we know Fe is nothing but pi square E by Le square, Lc by R whole square. So that is pi square into 29 10 power 6 divided by your slenderness ratio was 9.012 whole square, correct? And that is like 33.8 KSI. Okay, so that is my Fe value. From the Fe, I still have to find out my FCR, and FCR is nothing but 0.658. Power Fy in this case is 36. Fe in this case, um, Fy is 36 KSI, and Fe, sorry, Fe here is 33.8, right? And you find out your FCR is 26 point, oh sorry, times 50 ks, not 50, times your Fy, which is 36 KSI. Okay, so that's 26 point. Let's calculate this one here. So 0.648, 36 divided by 33.8, 0.658 expressed by that, then times your 36. So this is like 23.051 KSI. Okay. So that's your critical stress. What do you do with the critical stress? You find, if you have to find your nominal capacity, you take your critical stress 25.051, multiply with the gross area of cross section. The gross area of the cross section in this particular case is 8.76. So times 8.76 is going to give us 201.9 kips as your nominal strength. But we need to find out phi times of Pn, which is nothing but phi times of FCR times of A gross, which is nothing but 0.9 times this particular value here to 0.1.9. So reduce 10% from that, and you end up with 181.73 kips. So that is your phi Pn, and your Pu is in the problem statement, I think 170 kips or 170 kips. So the strength is this much, but the load is only that much, because phi Pn, so Pu is less than phi times of Pn. That means we are good. Okay. So that's the first problem here. Again, let's quickly review it. We need to we have been given an HSS section. This is where we found out all the, to do anything with the section, you need to first pull up all the relevant properties. We pulled up the properties, and we are trying to see if we have to design it per E7 or E3 section in the code. That depends if you have slender elements or if you don't have slender elements. So to find out if you have slender elements or not, you need to pick up the B by T value of the section, compare that with an upper limit, which is also in the code. We talked about it in our previous session. There is a table in section B4, and that table has information about compression elements, members subjected to compression and also members subjected to flexure, and you have to pull up the limits from this particular section here. Okay, so you pull up the limit is 1.4 E by Fy, that is the upper limit. So upper limit is 39.73, whereas B by T ratio that we currently have is only 24. That means B by T is less than the upper limit of the slenderness ratio. That means we don't have a slender element in the HSS. When I say slender element, we are talking about just the elements that make up the HSS section. We are not talking about the entire height. we're not looking at the global slenderness ratio. We're just looking at local slenderness ratio, comparing it the local slenderness ratio with a limit, and deciding if we have a slender element or if we don't have a slender element. Okay, so we don't have a slender element. That means local buckling is not an issue. We only have to check flexural buckling, and flexural buckling is a pretty straightforward. There's a pretty straightforward equation. You need to figure out that, I mean, this graph is what has to pop up in your mind when you're dealing with compression members. You want to understand if you fall on this side of your graph or line of that limit, or if you fall on this side. If you fall on this side, elastic buckling will happen. If you fall on this line, inelastic buckling will happen. Okay. Um, so that means this is my cutoff. I find out my LC by R, and I compare that with this particular limit here and see if I fall on the left side or right side. In this case, else my LC by R is less than that value, so that means I am falling. That means I am in this section here. So inelastic buckling is bound to happen. I calculate my FCR value based on this equation. That is nothing but the equation of this piece of that curve there, right? You find your FE value. FE is that much. From FE, you find your FCR, because remember, FCR is a function of your FY and your FE value. So you find your FCR value. After you find the critical stress, you take the stress, multiply it with area to find your force. That is your nominal strength, and then reduce it with a factor of 0.9 to come up with your um, uh, design strength. Okay, you compare the design strength with the applied load and take a call if you are safe or if you are unsafe. Okay, so that's our problem 1. Now let's see what we have for problem 2 here. Problem 2, pretty simple, straightforward problem, but it's gonna teach us a lot, right? So that's problem 2, super simple. We just have a column. We have a W12 by 58 column, 24 feet long, pinned at both ends, braced in the weak direction at 1/3 height. Okay, that means you have an I section like that, right? And imagine this is the strong axis, and this I section is running like that, correct? I section is running like that, and it seems it is pinned at the bottom here, pinned at the top there, right? But then so this is the weak direction. It is braced along the weak direction at 1/3 height. So I'm going to draw weak direction supports in this direction and that direction, right? So it is supported here. We don't know what it is supported. Maybe it is supported with a let's say maybe it is supported with an HSS or an I section or whatever. Okay, we only know that we have a brace in that height. Okay, so that means this height from here to here is your 24 feet, whereas because it is braced at every 1/3, that means that height from here to here is 24 by 3, which is 8 feet. Okay, so from here to here is 8 feet, from here to there is another 8 feet. Okay, again, this is strong direction, this is the strong XX, strong axis, right? And then that line there is the weak direction, which is YY. And in the weak direction, we have these braces. Okay, so how do you calculate the strength of a column? Before you do anything, you pull up your properties of the section, which is in this case W12 by 58. I can show you which table, but I don't want to get into all those details. I'm assuming you know how to pull the properties from the code here, right? If you pull the properties, you'll see that Ry is 2.51, okay, and Rx by Ry value is like 2.10, right? Which implies Rx is nothing but 2.1 times of 2.5, correct? Because this is 2.51, because this is 2.51. It's nothing but 5.271. Okay. You need these, and you also need your, because it's a compression member, you have to multiply the FCR with AG. You also need your area of cross section. That means area of that hatched portion there, right? You want your gross area of your compression member. Okay. Now you find out. Your LCY by RY, correct? And you also find out your LCX by RX, and pick up the maximum. So max of these is your slenderness ratio. So LCY by RY, LCY is 8 feet. LCX, sorry, LCX is your 8 feet. Okay. So let's do LCX. LCX is your this height about the strong axis, right? So you have 24 times 12 divided by Rx, which is 5.271. That is close to 54.638. So that is one slenderness ratio. The other slenderness ratio is in this direction, in the y direction. Y direction, the height is only 8 feet times 12 divided by your Ry is 2.51. So this is 38.24. Okay. So the maximum slenderness ratio is this particular value here, right? Because we have to pick up the LCR by, we have to pick up LCR maximum, correct? So your final LC by R is max of your 38.24 and 54.63. So that is nothing but 54.63. Okay. Now what do you do with your oops, I think I'm drawing it on the screen here. Okay, anyway, what do you do with your LC by R? You have to first find out your FE value, which is nothing but pi square E by LC by R whole square. That comes out to pi square. E is 2910 power 6 for steel, and your LC by R is 54, maximum value 50.63 times whole square. So that is 95.87 KSI right there, FE. Okay. Then you find out your limit, which was 4.71 times E by Fy, right? E is 2910 per 6. Fy, you know that this is what steel was it? I think that information was it missing. Okay, so let's treat this as a 50 KSI steel. Okay, so grade 50, which means your Fy is 50 and Fu is 68 KSI. Okay, so you take that and you compute this limit, you substitute those values, and the limit comes out to be 113.43. Okay, my LC by R is only that much. It is much it is less than your 113.43, which is upper limit. That means, like I said, you are on this is your limit. It is 113.43, whereas this is 54 point something, so we fall on that side wherein our inelastic buckling is gonna happen. Okay, and so when inelastic buckling happens, your FCR is 0.658 Fy by Fe, right? And you substitute 0.658, you calculate your Fy, sorry, Fy is known. Fe, we calculated it as 95.87 Fi by Fe, correct? And this comes out to FCR, comes out to be 40.19 KSI. Okay, so once you calculate FCR, you calculate your phi Pn as phi times of FCR times of A gross, right? Phi is 0.9, you know your ACR, you know your A gross, substitute all those values and you will end up with 615 kips as your strength of W 12 by 58 column with an which is governed by your LCX by R value of that much. Okay. So again, just to recap, we have been given 12 by 58 column. The length of the column is 24 feet. It is pinned at top and bottom. The column was pinned at bottom and also at the top, and that entire height was like 24 feet, correct? But then it is braced in the weak axis at 1/3 height. 1/3 height is 28 by 3, which is 8 feet. So bracing in the weak axis is, I mean, the length in the weak axis is like 8 feet, but length in the strong axis is 24 feet. And that's what you're using. Length in the weak axis 8 feet, length in strong axis 24 feet. You find out your lambda ratio in the weak and strong directions and pick up the maximum slenderness ratio, which is that much, and you use that slenderness ratio to calculate your Fe value. That comes out to be 97.58. You compare that with the limit, which is 113. You realize that you fall on this side of the curve, and then you use the equation of that portion of the curve, which is nothing but your 0.658 Fi by Fe, right? Times Fi. I think that is missing here. Okay, once you do that, you'll get 40.19. That is your FCR. How do you find your nominal strength? Strength reduction factor of 0.9, FCR of 40.19, A gross of 17.10 inches, and you find out that your section is that strong. Okay, so that's our second problem. Let's do another problem. This is an interesting, simple, but a nice problem here, right? So I think imagine you have, sorry, imagine you have a frame like that, correct? And there are a bunch of columns and beams, right? And your bottom column is fixed, right? So this particular column here is column A, and let's call this column as column B. Okay, and so that beam there, the section property of that beam there, so that beam is a W18 by 40. Same thing with this beam. This beam here is W18 by 40. Okay, but the column is W12 by 58. So let's say all these columns are W12 by 58, correct? So this is also W12 by 58. Okay, now we have been asked to determine, now let's read the problem. Use the alignment charts to determine the effective length factor. Effective length factor means you have to determine the K value of column A and B. We will only do A, and B is, I'll only do A, B is up to you. But the procedure is pretty straightforward. Okay. So firstly, you have to realize that this frame is not a sway frame, right? So this is not sway frame, because we have two types of alignment charts. And then firstly, I'll show you where they are hidden. They're hidden in a commentary section, right? In an exam setting, when you have to pull up all this, I mean, at office, you can use any tool you want, right? But then and pull up this information quickly. But in exam setting, all that you have is a code book, and you need to find out how you can find these values. Okay, but anyway, so how do you find the K factor for this particular column here? You know that the K factor is a function. The K factor that you need to find will come from alignment charts, but you have to enter the alignment charts with something called GA and GB values. Okay, you enter the alignment chart with those values, then you can find your um, um, K factor for that particular column. Okay, so G sub A is nothing but sigma E column, I column divided by L column, right? Whole thing sigma should be outside, like sigma of E beam, I beam, L beam. Okay, L beam, for example. Okay, now for this column here, you only, I mean, GA value is being computed at the top, and then we come here and calculate GB value. So at the top, if I have to calculate GA, then I only have one column. So my E times of my um, I value for column 12 by 58 divided by my length of my column here, right? So I think that is missing here. So this is 13 feet, and let's say this is 25 feet. All these things are 25, and this is also 13. This is also 13, and this is also 13. The height of the column, right? So the height of the column is 13 feet. So 13 feet times of what, 12 in inches, right? Because your E value, but that is the only column there. Whereas there is a beam on the left side here, the beam on the right side here. So you have two beams, and the assuming the material E of the column concrete and beam concrete is same, you have E times of I of your 18 by 140 divided by the length of that beam, which is 25 feet times of 12 inches, right? So that is nothing but, so you need to find out your member properties now. Member properties, okay. So for my I or W 12 by 58, my moment of inertia seems to be 475 inch power 4, and my W 18 by 40, which is my beam, 612 inch power 4. Okay, so come here, substitute those values, right? It's nothing but 475 divided by the length of column 13 by 12, 13 times this one, and flip this and multiply, so you get your 25 times of 12. There's a 2 here, right? Yeah, and then divided by 612 times 2. Okay. Okay, so you compute that, and you find out that this is 0.746. Okay, the same thing, we repeat the same process, but now we calculate your GB factor, which is at the bottom of the column there. So at the bottom column you have two beams with x more or less that much, and these are W sections. You will have to find the moment of inertia of the W section I12 by 58, right, divided by the length of that column. Sorry, the length of that column is 13 feet in inches. So that is nothing but sigma E column I column by L column, right? And we have two, so that's why there is a 2, right? And then at the bottom you also have two beams framing into that joint there. So your 2 E I beam is I of, you have to find the I value of moment of inertia of that divided by your 25 feet times of 12. Okay, so you find this value, um, nothing but 475 divided by 13 by 12, flip and multiply 25 by 12, 25 times 12, these are the lengths, and divided by 612, you end up with 1.5 value. Okay, so that means we found out our GA value. The GA value was 0.746. We found out our GB value. The GB value is 1.5. Now you have to get into the alignment chart. Okay, so the alignment chart um, is hidden uh, in I think one of the appendix commentary section of the appendix, right? So here is a commentary section, and you get into appendix 7, and that's where the alignment chart is hidden. So this is for an individual column, but our column is in a frame. This particular thing here is for, yes, for column in a frame, but then sway is inhibited, meaning you have something like that, but then maybe you have a brick wall or a bracing or something like that, right? So the sway here is inhibited, but that's not where we are. We are in this particular section here, and if we draw a line between, remember our Ka value, so this is our Ga, this is Gb. Our Ga was 0.746 and our Gb was 1.5, right? So GB 1.5 is here, GA 0, 0.2, 0.4, 0.6, 0.8, so 0.75 somewhere there, right? And then you come back and put a line here, and then that means you are between this value and that value, 1.1 to 1.3. This is 1.3. This is 1.4. So your final K value is 1.3 plus roughly 1.4 by 2. I'm not doing it exactly here. So let's say 1.35. So that is the effective length factor for that particular column, which was right. So this for this particular column, piece of column here, because you have so so GA is value there, GB is the value here, right? And when we calculated GA, in the numerator you have one column, and in the denominator you have two beams, properties of two beams. When we calculated GB, both the numerator had two columns and the denominator had two beams. Okay, so we compute that. So that's the end of this particular problem. We found out from the alignment chart that our K is 1.35. Okay, so quick recap. We have been given a column here. We have been given a couple of beams. The properties of those beams and columns are all here, right? So the property of the beam is here. We had to find out the effective length factor. Now, where do you use the effective length factor? Let's say you want to find the phi Pn of that particular column. Then you need FCR times of A gross, right? But you know that your FCR is a function of your Fe and Fy, okay? But your Fe is nothing but pi square E by Lc by R whole square, right? Now your LC is K times of L, okay? So in the exam, they'll ask you just phi Pn, what is my capacity of the column, but then of this particular column, but then you'll have to realize all these dependencies and then carefully plug and check all these values. Okay. So in short, we are finding GA at the top, we are finding GB at the bottom, and then we are going to our chart, which is sway sway uninhibited, because this column, we don't see any bracings in this beam, we don't see any shear wall in the problem description, and then we pick up our value from there. Okay, so that's about problem 3. So let's do another problem. You can have infinite amount of theory, but if you can't solve the problems, virtually it's virtually useless, right? Okay, so what do we have in this thing here? We have problem 4. Oops. Problem 4. Determine the strength of a single angle. Wow, single angle section. It's a part of a truss assembly. This is the angle size, and then welded through longer leg, and then we are given some information about the steel. So maybe this is just an angle within a within a truss, right? So here is the angle. We have been asked to calculate the capacity of that angle, the load carrying capacity of that angle. The angle is L4 by 3 by 3 by 8, right? And then the long leg is connected. So the connection is made through the long leg. So if this is your angle, right? That is your 3 dimension. That is your 4 dimension right there. The connection to some other member is made along the long leg. Okay, because remember we looked at angles in our previous session, and to find out the LC by R value of your angle, the actual LC by R value of the angle, you need to understand if the angle is connected through its long leg, if the connection is made through the long leg, or if the connection is made through the uh, short leg. Okay, let me walk you through real quick and see if you can recall these details. So angle compression member right there, right? So single angle member. If you see this is for single angle compression member. you first need to check if your b by t value, I mean, the angle can be a slender, can have slender elements, right? So you'll have to check if your b by t of your angle is within 0.71 square root of e by fy, okay, is less than that value. If it is less than that value, then we don't have to consider flexural torsional buckling, right? So if that value is there, then your ftb will be out, okay. So now you are left with just flexural buckling or um, um, just with flexural buckling, because we are FTB is anyway gone. Okay, so FTB flexural buckling is pretty straightforward, like how we did in our previous equation. You take FCR Pn, you find out your FCR and you multiply it with Ag, you multiply it with the phi value. That's how you calculate this one. Okay, but for your FCR calculation, you have to find out the actual slenderness ratio, which is LC by R. Okay, so for an angle, what they are suggesting here is if you meet all these conditions, you can neglect the neglect the eccentricity, because when you load the angle, you're not let's say this is the angle, you're not loading it concentrically. There's some amount of the centroid might be somewhere there, but you are loading it elsewhere, so there is small amount of eccentricity. Okay, so that means we are trying to amplify the LC by R value and then make our life easier. Okay, how does that amplification happen? Amplification happens in this particular section. Your columns are connected to longer leg. You will have to see if you fall here or if you fall here and pick up the right equation. Um, in our case, I think the angle length, the length of the angle was 72 inches, right? And there's something called RA, which is very important. RA is your radius of gyration, but then you need to figure out about y-axis, about this axis here, or about that axis, about the x axis here. Okay, so the connection in this particular problem is made with respect to the longer leg. So RA is nothing but the slenderness ratio about the axis parallel to the longer leg, which is in this case RA is nothing but RY. Okay, so you find out the ry. In this case it is ry. So in some other problem it might be, if you were to connect it with your shorter leg, then it would have been rx. Okay, um, but I'll take you there. But then our ry value, ry is nothing but 0.873. But the idea is to calculate the L by RA value, right? So in this case, if you calculate your L by RA, which is 72 divided by your 0.873, this is 82.47 for the angle that we are talking about, which is greater than your 80 limit. So this doesn't apply. So you'll get here and you'll actually find out your LC by R value. Okay, so LC by R value, again for an angle, you will have to amplify it based on this equation or based on this equation. You cannot just pick up your you cannot just look at your boundary condition and then take an effective link factor and then find out your LC by R. You will have to amplify because the angles are not loaded concentrically. Okay, so let's go back, continue the problem here. Um, so first you find out your member properties of that particular angle. Okay, so properties of L4 by 3 by 3 by 8 inches. Again, everything is available in the steel table, but the most important properties are your IY appears to be 1.89, SY appears to be 0.851, RY is 0.873, X bar may not be useful, but then because I am on that page, I am just noting it down so that I don't have to flip all the pages. Okay, Y bar is 1.52. Okay, area of the angle, gross area is 2.49 inches square. IXX is 3.94, may not be needed. RX is equal to 1.44. I am on the page. I don't want, before I get into a different page, I want to note stuff down. ZX is equal to 2.6. Okay, and my b by t of my angle is 4 by 3 by 8, which is nothing but 10.667. Okay, so to solve, now I'll start my solution, correct? And when I start my solution, I want to see if this angle has slender legs or not, right? Remember, we talked about that one condition wherein flexural torsional buckling can be neglected if a certain value is, if the b by t is less than 0.7 square root of e by fy, right? And that is exactly what we are checking here. 0.7 square root of e is 29 10 power 6. Your fy value is 15 to 10 cube, right? Um, so this is 10.667, whereas this one comes out to be, this whole thing comes out to be 16.85. So that is 10 points is less than 16.85. Okay. So that means what? Why did we do this exercise? Just to eliminate flexural torsional buckling out of the equation. Okay. So we are left with just flexural buckling. And to calculate flexural buckling, you need to calculate your LC by R value. You have to calculate L by RA first, and then see where you fall. We calculated that L by RA is is my L by RA. It is greater than 80. We found out that it was greater than 80, right? How? L was our 72 inches. My Rx was 0.87, Ry was 0.873. Now, why am I using, what is Ra? Why am I using Ry? Ra is about the axis parallel to the connection. So in this particular case, axis parallel to connection was Yy, right? So I'm using my Ry, which is greater than 80. So when it is greater than 80, my LC by R can be arrived from that equation, which is nothing but 32 plus 1.25 times your L by RA value. Okay, so that means here indirectly we are amplifying it. So 1.25 times of 82.47, so that is 135.0875. So this value is much higher than your L by RA value. So that amplification is what is we are trying to account for the eccentricity effect of that eccentricity via amplifying this particular slenderness ratio. Okay, now we got the slenderness ratio LC by RA. How do you calculate your FCR? Correct. You again you know that the FCR is on the y-axis there. Your slenderness limit, which is 4 point what was that, 71 square root of e by fy is here, correct? You need to find out if you are here or if you are here. So if you take the curve will be something like this. Should I use this equation to find my FCR, or should I use this equation to find my FCR? Okay, so that depends upon your LC by RA value. LC by RA is 135. That's what we found out, 135.08. Okay, whereas my 4.71 times of square root of 29 into 10 power 6 by 50 KSI, 50 10 cube, that comes out to be 113. So this comes out to be 113.43. So that limit there is 113. Oops. Okay, so that limit there, this limit is 113, whereas my value is to the right of it. So we are here. That means elastic buckling is going to happen. That means our FCR equation, if you go back to the code, 0.877 times of your FE value. Okay, so 0.877 times of pi square E by LC by R whole square, right? So 0.877 times of pi square, E is 29 10 power 6, LC by R, this value here 135.08 square. So that is roughly 13.75 KSI. Okay. What do you do with FCR? You multiply it with the area of gross. So phi PN is nothing but 0.9 is my phi. My PN is nothing but my FCR, which is 13.75 times of my gross, which is 2.49. That is nothing but 31 kips. Okay, so there's that. I mean, this is the uh, longhand way of doing things. But if you want to, in an exam setting, sometimes there are a bunch of tables which are useful. So if you want to know how those have to be used, leave a comment, and then I will try to see how I mean try to use the tables on one of these problems, and we go from there. Okay. So we covered a bunch of problems today. We covered a lot of theory last time in our uh, discussion of part 4 and chapter E. We talked about I mean, the problems that we talked about are a simple HSS section. This might be a case wherein you have a beam and you're just putting a HSS column underneath, and then you have a ladder bar truss or something like that running under on the top. So you need to find out the strength of this particular HSS column. Yes, you can use a computer software, but how do you do it manually, right? So this is 8 by 8 by 5 by 16. How do you find the capacity of that column? So that is an example that is here. And then we talked about another example. This case, you have an I section like that, and the I section is being supported differently in different directions. In this direction, you have support coming there, you have support coming there, which is in the weak axis, whereas in the strong axis, the I section doesn't appear to be supported along the entire 24 feet length, I think, on the problem, right? This was 1/3, which was 8 feet, 8 feet. So what we did here, we found out our slenderness ratio in both the directions, and we tried to calculate the capacity of the column there. Okay. Now the third problem, this might be super common, um, wherein maybe you have a truss like that being supported by a couple of columns, and that um, truss has elements like this, and all these elements are made out of angles, right? Now, how do you find the capacity of the angle? From structural analysis, maybe you know I mean, from just based on hand calculation, you know the load coming onto the column, but then how do you qualify that particular angle, right? So we went through angle. I mean, this particular case, the angle, the longer leg of the angle was connected to the connection, right? Was welded to the connection there, and then we found out we don't use I mean, we calculate the LC by R values based on LC by RA values, and we talked about all those details, and then how you can calculate the strength of that particular member here. Okay. All right, that's all I wanted to cover in this video. Thanks for watching.